How nice to see that you are here and that this topic is drawing your attention. I will briefly introduce myself. There are my speaker notes. Then I will say or explain something about what is a quantum computer, why we should monitor the events of the quantum computer, what are the known complications, the known unknowns, and last but not least, we have also some converting certainties, and last but not least, I will share some low regret moves you can take. First of all, I'm active in the payment industry since August 2001. I was for more than 12 years responsible for the certification program of the Dutch payment terminal. Today I'm a cybersecurity analyst for the Dutch Banking Association, chairman of the Dutch Interbank Security Working Group, and member of the curriculum committee that organized a course Applied Cryptography. I'm also chairman of the ECPA Security Working Group and member of the PCI PTS Working Group. This is a picture of a quantum computer. You will see that this will not arrive on your desk anytime soon. It is very fragile, it's very sensitive for environmental influences, and it uses quantum mechanics to process information. It uses qubits, which are very fragile. At the lower part, at the chandelier, there's the processor, which operates at 30 millikelvin. And that is more or less minus 273 Celsius. So very chilly. In operation, you will not see this beautiful chandelier. It is hidden in a refrigerator. To understand something about a quantum computer, you must know something about quantum mechanics. There are three important concepts. Superposition, that is a very difficult concept. Let's give an example which comes close but is not quite correct. If I toss a coin, as long as this coin is in the air, it could be head or tail. Once I catch the coin, it is determined whether it's head or tail. In superposition, a particle really has two states at the same time. And when you do an observation, then it collapses and the state is determined. Particles can also interfere with each other, and behavior can be amplified, but can also be cancelled. And we have entanglement. Particles can be entangled, and once they are entangled, they become one system. And even if you separate the particles over a large distance, thousands of kilometers, it still is one system. And do you an observation on one particle, both collapse at the same time. So our current computers make use of bits. They are either 1 or 0. Quantum computers make use of qubits. They are 1 and 0 at the same time. And every time you add a qubit, the computational power doubles. So that ramps up very rapidly. If the quantum computer becomes available, it will not be unnoticed. It will be a disruptor. Let's give an example. A quantum computer can simulate the properties and behavior of molecules. Sorry. An important part for making a virtualizer is nitrogen fixation. This is one of the most expensive processors to operate. It consumes 2% of our energy worldwide. But in nature, bacteria are able to do the same operation at room temperature and atmospheric pressure. So there's a lot to gain. But we are not able to simulate it on a supercomputer. We are running out of memory and running out of computational power. However, Raya and others showed that a quantum computer with only 111 qubits are able to simulate this process and reveal the secrets. So if that becomes possible, chemistry, but also pharmacy, will make a huge leap forwards. Okay, but why should we monitor the developments of the quantum computer? Now, security brings us together here. And to secure data and transactions, we often make use of encryption. Symmetric encryption is very fast, but has a large disadvantage. The key to encrypt and decipher is the same. So every time you want to exchange a key, it is always tricky. And for every communication partner, you need a different key. So symmetric encryption often leads to key management challenges. At the other hand, we have asymmetrical encryption. It's very slow, but it offers us a lot of flexibility. We can use it to monitor integrity of data. We can use to sign data. We can organize non-repudiation. And we can use it to exchange keys. If we look to our business applications, almost all of our business applications make use of both symmetric and asymmetric encryption. And in general, we can say that encryption raises a barrier, and this barrier is tailored on the computer architectures of current computers. A hard problem for our current computers is not always a hard problem for a quantum computer. Some hard problems are easily solved by a quantum computer. There are even 2 algorithms known that can weaken our current encryption ciphers. The first one is the algorithm of Love-Grover. This can weaken our symmetrical ciphers. But if we double our key length, oh, we are fine. But this does not allow to double the key length, so we have to migrate to AES. For hash algorithms, if we double the output, we are fine. But the collision risk is not impacted that much. So if we use SHA-2 or more recent, we are fine again. But the Shor algorithm, that really will break our asymmetrical ciphers. Let's give an example. The hard problem for RSA is factoring. It is hard to find the original prime numbers of a large number, in example 2048 bits. If we use the best available algorithm to find the original prime numbers, GNFS, and we run it on a supercomputer, it roughly takes 10 to the power 34 steps to find the answer. If we run it on a supercomputer that operates 1 trillion operations a second, it still needs 317 trillion years to find the answer. In that case, we're quite safe. However, if we give the same challenge to our Shor algorithm, it roughly takes 10 to the power 7 steps to find the answer. If the quantum computer operates at 1 million operations a second, the answer is revealed in 10 seconds. In that case, RSA is broken. But we need a quantum computer with 4,099 logical qubits. And the strongest quantum computer I'm aware of is the one of IBM, which has 127 noisy qubits. We roughly need 1,000 till 10,000 of these noisy qubits to be able to construct a logical qubit. But how much time do we have? Should we panic? If you're managing state secrets, perhaps you have already a challenge, because your adversary can record all your confidential recording if you're using open internet or other open channels, and wait patiently till the day a quantum computer becomes available. Luckily for us, we process transactions. Once a transaction is processed, it becomes irrefutable if you have done it correctly. So in that case, the theorem of Michaela-Mosca comes at hand. Here the X stands for the security shelf life. What algorithm are you using in combination with that key length, and how long can you use it securely? The Y stands for the migration time. How long will it take to migrate from your current quantum vulnerable encryption cipher to a quantum resistant encryption cipher? If the quantum computer becomes available before you have finished your migration, you're in trouble. That is really well understood by NIST, and they organized a contest to find new quantum resistant encryption ciphers that can be run on our classical computers, which can replace our asymmetrical ciphers. The NIST competition is running, and we expect results between now and 2014, and hopefully that will be new standards we can use. But how long will we have? In 2015, Michele Mosca stated the chance is 1 on 7 that a quantum computer is able to break an RSA key of 2048 bits by the year 2026. And the chances will be 50% that a quantum computer is able to do so in 2031. Nobody knows the exact day. But what I like of this expression is that it expresses that the likelihood will increase over time. Recently, Michele Mosca repeated it and asked experts in the field, how much time do you think it will take? And they said, oh, roughly 15 years. But don't get us befooled. Often we overestimate the changes that occur in the next 2 years and underestimate the changes that will occur in the next 10 years. But assume we have 15 years. Okay. The known complications. Replacing a crypto primitive takes a long lead time. In example, if we look to a smart card platform, they have a service life from roughly 8 to 17 years. We select a smart card platform, we bring it for certification, we get an approval stamp for 4 years, and we can issue a card with a service life of 5 years, making 8 years. If we have selected the right smart card platform, we can run it for a recertification when the requirements still are met. We can do that 4 times, making 12, and the last card can again be issued for 5 years, making 17. Our smart card, EMV card, communicates with a point-of-sale unit or an ATM. They need at least to share one encryption cipher, otherwise they cannot communicate. The point-of-sale terminals have a service life of roughly 5 years. In the Netherlands, I think in average the point-of-sale terminal is 7 years old, used for 7 years. But ATM machines often serve longer. There are examples available where an ATM has served for 25 years. The most effective and cheapest way to introduce new ciphers is to make use of the ordinary replacement cycle. Of course, we can speed things up, but that will be more costly. And replacing ciphers by post-quantum crypto ciphers, they are not simple drop-in replacements. For optimal use, we have to redesign the protocols in combination with these new post-quantum crypto ciphers. And there are no standards available yet how to securely roll out these post-quantum crypto ciphers. Okay. But happily, we have also some comforting certainties. If we use a semantic encryption based on AES 128 and stronger, well, we're doing fine. If we're using hash algorithms like SHA-2 and more stronger, we're fine again. If we make use of functions like message authentication code, key derivation, and key generation based on these aforementioned algorithms, we're fine again. Also the protocols from the old area that predate the use of asymmetrical ciphers, where we had key custodians that brought in key material to extract a key. These protocols are secure. Oh, and we have a canary. The quantum computer will demonstrate its added value long before it will break our encryption. Remember our example with this nitrogen fixation. It will not stay unnoticed. Okay, the known unknowns. We still do not know when this quantum computer becomes available. The field of quantum computing and post-quantum crypto ciphers is in highly flux, and most of us do not have an inventory of the business processes that make use of encryption standards. So, based on this information, we have extracted 7 low-regret moves. The first one is a very obvious one. Monitor the developments of the quantum computer and post-quantum crypto ciphers. And better draw up frequently asked questions or a Q&A to be well prepared if media fires tricky questions. Secondly, make an inventory. What business processes make use of encryption? What kind of encryption standard is used, algorithm is used? What key length is used? Is this vulnerable to quantum attacks? What is a good alternative quantum resistant cipher that you can use which fits your business needs? And then look how much time it will need to migrate from your current vulnerable encryption cipher to this quantum resistant cipher. This will give you an indication where to start your migration. Third, ask the international organizations to prepare for the advent of the quantum computer. It is very helpful if there is some coordination. The payment infrastructures do not stop at the national borders, so some coordination comes at hand. But also look to your own supply chain. For semantic cryptography, start with the migration towards AES and SHA-2 and secure key derivation immediately. And it's really a no-brainer. And 5, the card payment infrastructure, develop a fallback system that does not rely on asymmetrical ciphers. I think that needs some explanation. It seems possible for point-of-sale and ATM machines to develop a fallback mechanism based on block ciphers and hash algorithms. We can use it for building blocks to construct message authentication codes, key generation, and key derivation. These are the ingredients to construct secure transactions. And of course, we can use a post-quantum crypto cipher for key exchange. And then it starts with the foundation. For a smooth migration, we would like to use a remote secure update. But for a secure remote update, we must use quantum resistant ciphers. So our operating system should also use quantum resistant ciphers. And on its turn, an operating system is loaded by a bootloader. So the bootloader should also use quantum resistant encryption ciphers. And then we run in an audit challenge, implementing encryption cipher in hardware. And Paul Kocher showed at the late 90s that it is a challenge. If a computer is running an encryption cipher and you're measuring the physical characteristics, it can be used to extract key material by just measuring time, power, electromagnetic radiation. Of course, we know how to defend our current encryption ciphers against these side channel attacks, but for this post-quantum crypto ciphers, it's a green field. So better start early and on time. And for our EMV smart card profile, develop a profile that does not rely on asymmetrical ciphers. Again, it sounds a bit cryptic, but if you process all the transactions online, real time, and you make use of AES, you're fine. And last but not least, enforce a policy to swiftly implement the latest TLS versions, because we expect that they will anticipate on time on the new standards and gain experiences with these new post-quantum crypto ciphers. Thank you so much.